Section 1. The Truth About Alzheimer's. In November of 1901, a young German physician named Alois Alzheimer was working at the Frankfurt Psychiatric Hospital when he was assigned a new patient. Her name was Augusta Dieter, and her husband reported that she was suffering from paranoid behavior, emotional outbursts, and increasing confusion. Some nights she would scream for hours, he said. Other times she was unresponsive. When asked to write her name, Dieter struggled with the letters, repeatedly saying, "I have lost myself." She seemed to have no understanding of time or place, and little to no short-term memory. Though memory problems in old age had been documented for centuries by the ancient Egyptians, Romans, and Greeks, Alzheimer had never seen or read about a patient with memory deterioration at such an early age. Dieter was only 50 years old. He took a special interest in her case, interviewing her and checking on her even after he was transferred to another hospital in Munich. Unfortunately, Dieter declined rapidly and died in 1906. When Alzheimer examined her brain, he found both amyloid plaques, abnormal protein fragments that aggregate outside of brain cells, and tau tangles, twisted protein fibers that cut off the supply of nutrients within brain cells. These same plaques and tangles are considered the hallmark pathology of what we now call Alzheimer's disease. Since this first case of Alzheimer's was discovered over a century ago, doctors, scientists, and researchers have hypothesized about the cause, the physical manifestations, and the solution to this terrible disease. Is it caused by a single gene? Can it be cured by a single drug? Does it progress suddenly or develop over a period of time? Is it modifiable or susceptible to changes in the environment? Are we stuck with the symptoms once the disease has taken hold? In asking these questions, and never being able to answer them with the research available to us, scientists and doctors have perpetuated some troubling myths about Alzheimer's disease that create a great deal of confusion and anxiety. That's why we need to begin by dispelling these myths and revealing what the research tells us. As you'll soon learn, the prognosis is not as dire or inevitable as we may have thought. Alzheimer's has many causes that are intertwined in a complex disease picture. Rather than a simple game of tic-tac-toe, Alzheimer's is more like three-dimensional chess. What matters is the combination of your age, your overlaying genetic risk profile, and how your lifestyle choices either protect or damage your brain. You can't control your age, you can't control your genetic risk profile, but you can control your lifestyle. You can control the health and resiliency of your brain, and by doing so, significantly delay or completely avoid the anguish of Alzheimer's. If all of us, doctors, patients, and leading researchers, understand that our lifestyle choices have a profound impact on cognitive function, we can abandon a wasteful approach doomed for failure, and we can stop the needless suffering. Chapter 1. Myths and Misunderstandings. When it comes to Alzheimer's, the most damaging myth of all is that lifestyle has nothing to do with the disease. Most of our patients are convinced that genes determine everything, that their daily choices have little to no impact on what happens to their brains. By the time they come to our clinic, they're already experiencing brain fog, short-term memory problems, and other symptoms of cognitive decline. They think that the process of decline started when their symptoms first emerged. The disease and the symptoms, they assume, must share the same timeline. But the truth is that Alzheimer's develops decades before a diagnosis. It's during those decades that the brain becomes increasingly vulnerable to what we eat, how much we exercise, our ability to manage chronic stress, the quality of our sleep, and the ways in which we challenge our cognitive abilities. Only later on, often when we reach our 60s or 70s, is the brain unable to compensate for our less than healthy choices. And that's when we first begin to notice changes in thinking and memory. The purpose of this book, and our life's work, is to make this connection clear, and to show you why lifestyle medicine, and specifically our NeuroPlan, is so effective at treating and preventing neurodegenerative disease. Common terms associated with Alzheimer's. Acetylcholine, a chemical messenger integral to learning and memory. Activated microglia, small cells that help with the clearing of waste and damaged neurons. ApoE4, a gene responsible for production of the protein apolipoprotein E, one function of which is to help regulate cholesterol in the brain. There are 3 types of apolipoprotein genes: ApoE2, ApoE3, and ApoE4. ApoE4 appears to increase the risk of developing Alzheimer's, and ApoE2 is protective against Alzheimer's. APP, amyloid precursor protein, which is found in many cell membranes, is a protein responsible for making amyloid, the abnormal protein associated with Alzheimer's disease. Atherosclerosis, hardening and narrowing of the arteries due to buildup of cholesterol plaques, which compromises blood flow throughout the body. Atrophy, the shrinking of an organ that results from cell degeneration. Beta amyloid, abnormal protein fragments that aggregate between brain cells and disrupt neuronal function. Brain-derived neurotrophic factor, BDNF, a protein responsible for the growth and proper function of neurons. Cytokines and chemokines, signaling molecules that support the immune system by attacking foreign substances. Dopamine, a chemical messenger involved in many behaviors like reward motivation and motor control. The decreased production of dopamine is a prominent feature of Parkinson's disease. Free radicals, molecules that are missing an electron and thus unstable and highly reactive. In the brain, free radicals can damage neurons and even DNA. Glia, the most common type of cells in the brain whose function is providing support and protection for neurons. Glutamate, the most abundant neurotransmitter in the brain. Inflammation, a naturally protective function of the immune system for fighting harmful bacteria and viruses. Acute inflammation helps us recover from injury. Chronic inflammation puts us at risk for diabetes, heart disease, and cognitive decline. Microvasculature, the smallest blood vessels in the body. Myelination, the process through which a neuron's connections are coated with myelin, a fatty substance that facilitates communication between cells. Neurons, cells that make up the nervous system, which includes the nerves, spinal cord, and brain. Neurotransmitter, a chemical messenger in the brain that facilitates communication between neurons. Oxidation, a chemical process that involves the transfer of electrons, thereby creating free radicals. Tau tangles, twisted protein fibers inside neurons that cause neuronal damage and contribute to Alzheimer's disease. Vascular health, the state of health of the vascular system, which includes arteries, veins, and smaller vessels. Lack of optimal blood flow to the brain due to atherosclerosis, hardening of the arteries, can starve the brain of oxygen and glucose, thereby accelerating the development of Alzheimer's disease. The 4 main pathways to Alzheimer's. 4 interconnected biological processes are responsible for most of the degeneration that contributes to Alzheimer's and other dementias. You'll see these terms throughout the book, so it's important to understand what they mean. The first is inflammation. Inflammation is a naturally protective function of the immune system for fighting harmful bacteria and viruses. Acute inflammation, the redness and swelling of a cut on your finger, for instance, increases blood flow to the injured area and facilitates healing. This type of inflammation is essential. Without it, we wouldn't heal. Chronic inflammation, on the other hand, occurs when the inflammatory response is activated long-term, often because of constant irritants like high-sugar diets, unmitigated stress, and many other unhealthy lifestyle choices. When inflammation is chronic, it turns from protective to destructive. Tissues are damaged instead of healed. The body actually attacks itself when inflammation goes unchecked. If you were to look at the brains of people with Alzheimer's even early on in the disease process, you'd see evidence of chronic inflammation in the form of cytokines and chemokines, proteins that support the immune system by attacking foreign substances, and activated microglia, small cells that help with the clearing of waste and damaged brain cells. Activated microglia become so hyperresponsive in clearing waste that they harm neurons, the cells of the nervous system, and their supporting structures, resulting in both cell death and structural damage. This is why chronic inflammation is widely considered a main factor in the development of Alzheimer's. The second process is oxidation. Oxidation occurs naturally when oxygen reacts with other substances, and by doing so, changes them. A banana turns brown when you leave it on the counter. This is oxidation, and this same chemical reaction happens in our bodies. Oxidation results in the formation of oxidative byproducts called free radicals. Free radicals are molecules that are missing an electron and thus unstable and highly reactive. Their high reactivity compels them to steal electrons from other molecules. In the brain, free radicals steal electrons from neurons, glia, cells that support neurons, and organelles, small cellular structures located within cells, as well as proteins, lipids, fatty acids, and even DNA, all of which results in permanent damage. Because the brain works harder than any other organ in the body, consuming 25% of the body's oxygen, it's especially vulnerable to oxidative reactions. The brain is also a kind of vacuum-sealed system. The energy to clear oxidative byproducts must come from within this system. There appears to be minimal outside help. Though the brain has special cells and molecules that help break down and neutralize free radicals, these cells and molecules are damaged over time by poor diet, lack of exercise, chronic stress, lack of quality sleep, and general aging. When the brain's natural clearance system is compromised, free radicals become especially harmful. Glucose dysregulation is another biological process that contributes to Alzheimer's and is especially common in the early stages of the disease. The system responsible for maintaining glucose often begins to falter as we age, especially when we consume a diet high in sugar and refined carbohydrates, though in some cases there is also a genetic component to glucose dysregulation. Abnormal production and usage of glucose affects the pancreas, hormones, enzymes, and cells that make up this bodily system. And because glucose is a major source of energy for the entire body, the consequences, like impaired immune function and inability to clear harmful waste products, are far-reaching. These negative effects are compounded in the brain due to its considerable energy requirements. One dangerous consequence of glucose dysregulation is insulin resistance, which is a change in our sensitivity to insulin, a hormone that allows our bodies to harness the energy of glucose, and glucose's most important regulatory mechanism. Glucose fuels our brain cells, but it can only be actively internalized or brought into the cell in the presence of insulin. When insulin binds to the cell's receptors are prompted to bring glucose inside. But when there's too much glucose in the bloodstream, two significant problems arise. 1. Insulin levels rise and cells become desensitized to its effects. It's as if there are fewer locks, receptors, for the key, insulin, to open. The result is that glucose levels rise outside of the cells, but because the receptors aren't working properly, glucose can't be internalized. The cells then end up starving from lack of glucose, even as the bloodstream is flooded with it. And 2, high insulin levels in the blood initiate a cascade of other harmful processes, including inflammation, oxidation, destruction of lipids, fats, and tau phosphorylation, which creates the aberrant form of tau protein strongly associated with Alzheimer's disease. You can find more information about insulin resistance in the brain in the nutrition chapter. Many people are unaware that they're insulin resistant, but this pathology alone can lead to cognitive decline and Alzheimer's. Once you've crossed over the threshold from insulin resistance to diabetes, the most dangerous consequence of glucose dysregulation, your risk of cognitive decline is even greater. Studies have shown that individuals with diabetes experience brain shrinkage in the hippocampus, an important memory center. Lipid dysregulation is the fourth biological process responsible for the changes that lead to Alzheimer's and dementia. Lipids are fat-like substances. They form the building blocks of cell walls, hormones, and steroids, and are integral to cellular structure, energy storage, and signaling, all life-sustaining functions. Lipids are also pervasive in the body, and especially in the brain, where they compose more than 50% of the brain's dry weight. Lipid dysregulation occurs when the body is subjected to excess lipids, inflammation, oxidative damage, and other forms of stress. In response, lipid transport and metabolism are impaired, which leads to lipids being oxidized, creating even more harmful oxidative byproducts. There are many disease-promoting effects of lipid dysregulation, but here we want to shed some light on two of the processes in the complex system that are relevant to Alzheimer's. 1. Cholesterol is a type of lipid whose processing and clearance is altered when exposed to stress. It begins to accumulate in the blood vessels, eventually forming plaques that clog arteries and cut off the blood supply to small vessels. The end result is microvascular disease, damage to our smallest blood vessels. Over time, macrovascular disease, damage to larger blood vessels, can develop as well. Both micro and macrovascular disease are downstream consequences of lipid dysregulation in the vascular system, and as you'll learn throughout this book, vascular disease is a major risk factor for dementia. 2. This improper clearance and processing of cholesterol and other lipids can also lead to a cascade of damage that ultimately contributes to the formation of amyloid plaques, the brain pathology strongly associated with Alzheimer's disease. ApoE4, the most researched gene connected to Alzheimer's, is also implicated in lipid dysregulation in the brain. This gene encodes a protein responsible for clearing both lipids and amyloid, but because this version of the protein is inefficient at clearing waste, lipids and amyloid accumulate outside brain cells and begin to damage neural tissue. Later in life, the cumulative trauma of lipid dysregulation, vascular disease, and improper clearance of amyloid, combined with years of inflammation and oxidative stress, can ultimately manifest as Alzheimer's disease. All four biological processes are interconnected, though Alzheimer's and dementia can be primarily driven by one or more of them. That is, neurodegenerative diseases have different pathways to the same end result. A person with a diet high in cholesterol and saturated fat may develop vascular disease first, which leads to inflammation and then oxidation, whereas a person with a diet high in sugar may start with insulin resistance, which then leads to vascular disease and inflammation. The combined effect of these processes in the body results in the formation of amyloid and tau. The cascade of biological changes comes first, followed by the physical pathology of Alzheimer's, except in rare early onset cases where amyloid and tau appear to drive the disease process. In this way, Alzheimer's disease is really a constellation of several different disease pathways that ultimately manifest in the symptoms and pathology we call Alzheimer's. What's so incredible is that all four pathways are deeply influenced by lifestyle. Our daily choices are the driving force at the onset of Alzheimer's and throughout the entire progression of the disease. As we'll show you in Section 2, each one of these pathways can be controlled and even reversed by how you live your life. With these biological processes mounting in the brain for decades, why don't cognitive symptoms appear earlier? How is the brain able to withstand daily assaults without showing signs of distress? The answer is that the brain is naturally and profoundly resilient. Redundancy is part of the brain's elegant design. With 80 to 90 billion neurons and close to a quadrillion connections, as well as overlapping arteries that supply multiple brain regions with nutrition and oxygen, the human brain can make pathways around damage. It can sidestep closed vessels and neurons destroyed by plaques, inflammation, and oxidation. If it takes a hit in the form of a stroke or injury, other parts of the brain can take over. Studies have shown that in strokes, for instance, parts of the brain near the damaged tissues compensate for lost function, as do mirror regions on the opposite side of the brain. The brain is also capable of regenerating some cells, though this capacity is limited. In Alzheimer's patients, cognitive symptoms emerge only after there is so much damage that the brain's innate resiliency can no longer compensate. This is what's so insidious about Alzheimer's. We only become aware of the disease once the damage is considerable. Despite the brain's tremendous ability to withstand damage, it is extremely sensitive to stress at the cellular level, especially in regions like CA1 of the hippocampus and the entorhinal cortex, both of which are implicated in memory. As we explained earlier in this chapter, the brain has a very difficult job. It consumes more energy than any other organ in the body as it processes input and interprets the world around us. It also has the greatest output in terms of heat, energy, and waste products. These waste products, including oxidative byproducts, are especially damaging if not properly cleared. But again, we can't see or feel the damage right away. It takes years for the trauma to accumulate, and during that time, we're usually focused on other bodily systems. In patients with diabetes, for instance, we monitor kidney damage, filtration, and the buildup of creatinine, all clear indications of glucose dysregulation. At the same time, elevated glucose in the blood is also destroying the brain's microvasculature, the smallest blood vessels, as well as billions of neurons and glia. In patients with cardiovascular disease, we address direct damage to the heart, vessels, arteries, and veins. Meanwhile, arteries harden in the brain, decreasing blood flow throughout. The brain really is the end organ of the body. Stress experienced elsewhere accumulates in the brain over time and ends up causing exponentially greater damage. Key facts about Alzheimer's. The past 100 or so years of research have yielded these key facts about Alzheimer's disease. Alzheimer's is a progressive disease of the brain that impairs memory, thinking, mood, and problem solving. Alzheimer's disease is one type of dementia that accounts for 60 to 80% of dementia cases. The majority of patients notice the first symptoms of Alzheimer's in their mid-60s to early 70s. Alzheimer's is grossly underreported on death certificates, making it likely the third cause of death in the United States. The pathology associated with Alzheimer's disease includes amyloid plaques and tau tangles in the brain, loss of connections between neurons, eventual atrophy or shrinking of the brain, inflammation, oxidation, glucose dysregulation, and lipid dysregulation are the main biological processes that drive the development of Alzheimer's. Alzheimer's and genes. Our bodies come preloaded with a set of key data points in the form of DNA. This genetic information is a product of our family's biological history. We inherit it from our ancestors. Most people have heard that Alzheimer's is an inherited disease, and because of this, they assume it can't be prevented or influenced. Our genes do in fact play a role in the disease process, but they are far from the only determinant. To date, more than 20 different genes have been implicated in Alzheimer's, most of them affecting immune response, clearance of harmful byproducts, and vascular health. But none of them guarantee that you will develop Alzheimer's disease. APOE4, the most researched Alzheimer's gene, is responsible for producing apolipoprotein E, a protein that helps regulate fats. Those who carry this gene are less resistant to Alzheimer's and may also experience an earlier onset by 15 to 20 years. Though having ApoE4 means you have a greater chance of developing the disease, Alzheimer's is not a foregone conclusion. Risk doesn't necessarily mean disease. To understand how ApoE4 affects our Alzheimer's risk, we first need to learn how genes work. Genes are stretches of DNA that determine specific traits. Each parent provides you with a particular form of any given gene. These gene variants are called alleles, and they can be dominant or recessive, where only one set of alleles determines the trait. Additive, where the alleles' characteristics add up to determine the trait. Or multiplicative, as in ApoE4, where the effect of multiple alleles is exponential. Let's look at a few examples. First, here's how dominant and recessive alleles determine eye color. Your father passes along a dominant allele for brown eyes, B, and your mother passes along a recessive allele for blue eyes, little b. Because B is dominant to the recessive little b, you will have brown eyes. Skin color is determined in an additive manner. The main gene responsible for skin color produces the pigment melanin, the amount of which determines the precise shade of our skin. Having fewer alleles, and therefore a lower level of melanin, means lighter skin. Having more alleles, and therefore a higher level of melanin, means darker skin. ApoE4 works in a multiplicative way, such that having more alleles exponentially increases your risk of Alzheimer's, and also lowers the age of onset. If you have no ApoE4 genes, you have the standard 50% chance of developing Alzheimer's at age 85. If you have one copy of the ApoE4 gene, you have a 50% chance of developing the disease at age 75. If you have two copies of the ApoE4 gene, you have a 50% chance of developing the disease at age 65, 20 years earlier than those without the gene. Individuals with two genes have 12 to 20 times the risk of developing Alzheimer's as those with no ApoE4 genes. It's important to note that none of these scenarios, even having two copies of the ApoE4 gene, which accounts for only 2% of the population, guarantees that you will develop Alzheimer's. If you don't implement healthy lifestyle practices, you'll have only a 50% chance of someday developing the disease. And for the great majority, adopting a brain-healthy lifestyle can completely eliminate your risk. For the other 10%, those with genes like presenilin 1, presenilin 2, or amyloid precursor protein, APP, that put them at an especially high risk, the effective lifestyle is even more startling. Consider Down syndrome individuals. Among those individuals between the ages of 50 and 59, 1 in 3 suffer from Alzheimer's disease. 50% of those over the age of 60 develop the disease. This increased risk of Alzheimer's has to do with how Down syndrome arises. Down syndrome individuals have 3 chromosome 21s, and the genetic code in chromosome 21 produces APP, a transmembrane protein responsible for making amyloid, the abnormal protein associated with Alzheimer's disease. These individuals therefore have a greater than normal amount of APP and the potential for higher levels of amyloid. Whether APP functions normally or contributes to the pathology of Alzheimer's depends on the action of enzymes, proteins that initiate or propagate chemical reactions in the body. These enzymes cleave APP into smaller pieces as part of the body's natural process of clearing amyloid. When this process goes smoothly, amyloid is cut and cleared away by the brain's innate waste disposal system. When this process goes awry, beta amyloid accumulates in small units outside of the neurons, where it then coalesces and starts to form plaques. These plaques cause inflammation that damages both cells and their supporting structures. Given the role of APP in forming amyloid plaques, we would expect almost all Down syndrome individuals to develop Alzheimer's, but they don't. Studies have shown that individuals with a lower prevalence of diabetes and heart disease have a lower risk of developing Alzheimer's, and also a later disease onset. Again, this is despite a genetic abnormality that all but guarantees Alzheimer's. As part of our work at Loma Linda, we're currently investigating which healthy behaviors confer the most protection against disease in Down syndrome individuals. By studying the risk factors common to all chronic diseases, obesity, inflammation, cholesterol metabolism, we hope to learn more about how to lower the risk of Alzheimer's no matter the genetic profile. Even more powerful proof that genes do not guarantee disease comes from studying identical twins in their 60s and 70s. Researchers at King's College London followed 324 female twins over the course of 10 years to investigate whether muscle fitness predicted changes in cognition. Despite the exact same genetic profile, the twin with greater leg muscle fitness experienced less cognitive decline than the twin who was not as physically fit. When researchers looked at the twins' brains using MRI, magnetic resonance imaging, they found that those with stronger legs had bigger brains. This study shows again that lifestyle changes, in this case exercise and muscle strength, can supersede genetic risk and dramatically influence cognitive health. Women and Alzheimer's. Many of our patients are surprised to learn that 2/3 of people with Alzheimer's are women. 1 in 6 women develop Alzheimer's after age 65, while for men the chances are only 1 in 11. Women in their 60s are twice as likely to develop Alzheimer's as they are to develop breast cancer. We don't know for sure why this is. Longevity is at least part of the equation. Women live longer than men and thus are more likely to develop the disease. But even when longevity is taken into account, women still seem to have a higher risk. Women who have the ApoE4 gene are twice as likely to develop Alzheimer's as men who have the same gene. Some researchers have posited that women have traditionally had less access to intellectually challenging jobs and higher education, both of which are protective factors against Alzheimer's. Women who have multiple children are at greater risk for stroke later in life, both mini strokes and regular strokes, and there is a clear relationship between vulnerability to stroke and vulnerability to cognitive decline. Hormonal changes during menopause also affect the brain at both the neuronal and vascular levels, which in turn could promote cognitive decline. The remaining 20 or so genes that have been implicated in Alzheimer's affect the processes that initiate and propel the disease forward. Some of these genes govern the immune system and can either slow its response, resulting in the buildup of waste products that damage the brain, or cause an overactive immune response, which subjects the brain to chronic inflammation. Other genes impair our clearance system, again leading to the buildup of molecules that harm neurons and their connections. Additionally, genes associated with lipid metabolism and vascular health affect the vessels supplying oxygen and nutrients to the brain, and can promote vascular disease, vessel blockage, and neuronal damage. While we don't get to choose the genes we inherit, we do have control over how those genes are expressed. This relatively new scientific concept is at the heart of epigenetics, the study of environmental factors that regulate gene expression by turning genes on and off. Epigenetics is concerned with all the life experiences that can affect how your genes are expressed, everything outside of genetics that influences your health outcomes. We know that genetics accounts for at least some of the risk of developing Alzheimer's, but epigenetics plays an even greater role in determining our cognitive fate. Research has shown that our genomes actually change over time when exposed to harmful environmental triggers like poor nutrition, sedentary lifestyles, pollution and chemicals, and chronic stress, both mental and physical. All these factors can influence the genes of developing embryos and the elderly alike. Whatever environment we're exposed to, be it the womb or an aging body that's been dealt some decades of unhealthy living, we are constantly subjected to epigenetic processes. New studies show that environmental stressors accumulate as we grow older, which makes epigenetics especially relevant for those in their 60s and 70s who want to age well and avoid chronic disease. One of the main biological processes studied in epigenetics is methylation, a metabolic process in which a methyl group is passed from one molecule to another, ultimately altering gene expression. This process is a critical aspect of the modification and elimination of heavy metals, which can be toxic in the body and brain, regulation of gene expression, regulation of protein function, and RNA processing, transforming DNA's genetic information into proteins. Changes in the prevalence of methylation in certain regions of our DNA have been implicated in aging and seem to be especially associated with neurodegenerative diseases like Alzheimer's. A deficiency in B vitamins, caused by poor nutrition, is a major contributing factor to impaired methylation pathways, suggesting that diet is critical to healthy detoxification in the brain. Epigenetics will have wide-reaching implications for complex chronic diseases like heart disease, diabetes, cancer, and dementia. We can combat all these diseases simply by reducing the environmental factors that put us most at risk: sugary and processed foods, pollutants and heavy metals, lack of exercise, and stress. Decreasing the amount of sugar in your diet, for instance, impedes glycosylation, another epigenetic process responsible for high inflammation, impaired adaptive responses at the cellular level, and oxidative stress, all of which damage the proteins and DNA of neurons. Physical exercise regulates many cellular processes, resulting in methylation changes that improve the metabolism of amyloid and oxidative byproducts in the brain. Exercise also boosts the genes that encode brain-derived neurotrophic factor, a protein responsible for neuronal growth, and promotes connections between brain cells. Every day we're learning more about how our lifestyle choices alter both the expression of our genes and our risk of someday developing a chronic disease. Epigenetics in action. Several important studies illustrate the role of epigenetics in the development of neurodegenerative disease. The Honolulu Asia Aging Study found that Japanese people living in the United States have a higher prevalence of Alzheimer's than those living in Japan. There was little genetic variance among the men in the study, so the increased risk of Alzheimer's can be attributed almost solely to the epigenetic influence of poor diet, lack of exercise, and other unhealthy behaviors that are common in modern American life. Other studies have shown that in the United States, children of immigrants from China and Japan live shorter lives and suffer from more chronic disease than those children who stayed in Asia. Here, too, the genetic similarity among subjects points to the epigenetic processes that promote disease. In countries like China and India, we're seeing the epigenetic consequences as people move away from traditional lifestyles and adopt more modern ways of living. Diets high in vegetables and grains have been traded for animal products, refined sugar, and saturated fats. Instead of moving throughout the day, people are more likely to be sedentary. All these unhealthy behaviors change our gene expression and promote chronic disease. These dramatic and unfortunate lifestyle shifts give rise to the paradox of affluence, so-called progress leading to more disease. China now has the world's largest diabetes epidemic, with 11.6% of adults developing this chronic condition, and many millions more with prediabetes. China is also ranked second for obesity, behind only the United States. Both diabetes and obesity are major risk factors for dementia, which is also increasing exponentially. Alzheimer's Disease International estimates that China
had more than 6.4 million Alzheimer's patients in 2009. Another review in 2010 found that roughly 9.19 million Chinese were living with dementia. China has a rapidly aging population, a severe lack of nursing facilities and specialists, and little understanding of the challenges of Alzheimer's or how lifestyle affects the disease. India is experiencing a similar increase in Alzheimer's cases. More than 4 million people in India have some form of dementia, and that number is projected to increase dramatically as the population becomes more urban and influenced by Western lifestyles. In India, as in so many other developing countries, Alzheimer's and dementia are underdiagnosed and poorly understood. We fear these countries are not equipped to handle the explosion of lifestyle diseases that awaits them. This is why an understanding of the epigenetics of neurodegenerative disease is so critical to addressing the global epidemic of Alzheimer's. Alzheimer's and age. When Jeanne Calment turned 90, she decided to sell her apartment in Arles, France, figuring she only had a few years to live. Eventually, she struck a deal with her 47-year-old lawyer, who agreed to pay her a monthly rent until she passed away, which would allow him to acquire the apartment for a bargain. Calment's lawyer died of cancer 30 years later, having paid more than double the apartment's value. To everyone's surprise, Calment was still alive. She even lived on her own until her 110th birthday. When Calment was 118, she underwent neuropsychological testing and a brain scan. Her cognitive scores were consistent with those of people in their 80s and 90s. Her brain showed no evidence of neurological disease. Another enduring myth about Alzheimer's disease is that it's a natural consequence of aging. Research has definitely shown that Alzheimer's is a unique process of degeneration, and we have numerous examples of people living long, even extremely long, lives, and never developing the beginning stages of cognitive decline. Yet age is still a major risk factor. The older we get, the more likely we are to develop Alzheimer's due to the inflammation, oxidation, glucose dysregulation, lipid dysregulation, and other forms of stress that accumulate over time. Each decade of life has the potential to cause the brain significant stress and predispose us to developing Alzheimer's later on. In early childhood, physical and emotional trauma can cause considerable stress. Atherosclerosis, hardening of the arteries that supply oxygen to the body, starts during childhood because of lifestyle factors like poor nutrition and lack of exercise. Perhaps not surprisingly, physical neglect and emotional abuse sustained at a young age have been associated with memory deficits in adulthood. Most of the brain's myelination, the process of coating the neurons' connections with fatty cells called myelin, which facilitates communication between cells, and cellular growth, happens in our first 5 years, though myelination continues through our teens and early 20s. Both myelination and the number of cellular connections help the brain develop its resilience in the face of later traumas. Stress has been shown to significantly affect growth in developing brains. This means that if you have fewer connections and less cognitive resilience to start with, you'll have a much higher risk of developing dementia once you reach your 60s and 70s. Children who experience early trauma are also at a much higher risk for lifestyle intermediary diseases, like high blood pressure, diabetes, and high cholesterol, which increase their risk later in life for both stroke and Alzheimer's disease. Sports-related head trauma is another risk factor that can predispose children to developing cognitive problems. A 2013 study in radiology found that repetitive heading in soccer was associated with structural changes in white matter that could later contribute to cognitive decline. In our 20s and 30s, we continue to accumulate the early traumas to our brains that push us into risk. During these decades, many of us experience academic and professional stress, subsist on unhealthy foods, and often skip both exercise and sleep. All of these behaviors set the stage for declining health in midlife. As we progress into our late 30s and 40s, we may see the first signs of chronic disease, high blood pressure, high cholesterol, prediabetes, all of which adversely affect the brain. Later on, in our 50s and 60s, cumulative vascular disease emerges in the form of cholesterol plaque buildup, microvascular damage, and mini-strokes so small we don't notice them. The brain's waste disposal system also gets overwhelmed with inflammatory byproducts and other toxins, which promotes the buildup of amyloid and tau. By the time we reach our 60s and 70s, the hallmark signs of the disease begin to show up in MRIs and other laboratory tests. The first indication of Alzheimer's is the presence of beta-amyloid plaques, which usually emerge in our 60s. Tau intracellular tangles form shortly thereafter, usually in our 70s. Both of these toxic proteins cause hypometabolism, where brain cells use glucose, their main fuel, less efficiently, especially in the temporal and parietal lobes, two areas of the brain that are uniquely susceptible to Alzheimer's. Changes in metabolism then cause changes in structure. The brain loses connections, neurons, and overall volume. And the hippocampus, which regulates emotions and short-term memory, and other key regions of the brain start to atrophy. This is when we finally begin to experience the debilitating psychological and cognitive effects of Alzheimer's. Impaired memory, especially short-term memory, executive function, our ability to perform complex tasks, and visuospatial sense, the brain's ability to quickly and accurately interpret what it sees. Though there are instances of early onset Alzheimer's, when the disease emerges in the late 40s and early 50s, and amyloid and tau begin accumulating in the 30s and 40s, these cases are extremely rare. Generally, the disease appears after the 6th decade of life, once the brain has accumulated enough trauma to make its damage known. As we enter our 80s, we are even more likely to experience these cognitive changes. The longer we live, the greater our risk. FDA-approved medications for Alzheimer's. To date, the FDA has approved 5 medications for the treatment of Alzheimer's symptoms. Cholinesterase inhibitors, Aricept, Exelon, and Razidine are used in early to moderate cases of Alzheimer's and are designed to target short-term memory loss, confusion, and impaired thinking and reasoning. This type of medication works by preventing the breakdown of acetylcholine, a chemical messenger integral to learning and memory. Cholinesterase inhibitors do not stop Alzheimer's from progressing, but they may lessen symptoms for a limited time, an average of 6 to 12 months for roughly half of patients, though there are rare cases of symptoms lessening for up to 4 years. The other half experience no effect. In more advanced Alzheimer's patients, memantine, Namenda, can help block a specific type of neuron receptor called NMDA, which binds to glutamate, the most abundant neurotransmitter in our brains. Some people experience a slowing of the symptoms of cognitive decline, but this effect is only temporary. Namzaric is a new combination drug, a mixture of Aricept and memantine, and is sometimes prescribed for people with moderate to severe Alzheimer's. All these drugs can have debilitating side effects: nausea, vomiting, dizziness, nightmares, headaches, and they have no effect whatsoever on the progression of Alzheimer's. The newest drug in development, aducanumab, has shown some promise in a group of 166 people. It effectively removed amyloid without the severe side effects of other medications. In a small subgroup of 40 people, this drug was shown to significantly slow the progression of Alzheimer's, but several studies have demonstrated similar results that could not be replicated in a larger group. A Phase 3 clinical trial is now in progress, with results expected by 2020. The failures of Alzheimer's research.
A recent study published in Alzheimer's Research and Therapy examined all Alzheimer's clinical trials that took place between 2002 and 2012. Researchers found that 244 compounds were tested during this decade in a total of 413 clinical trials. Of these compounds, only one drug was approved: Namenda, a glutamine blocker that can temporarily lessen some of the symptoms of Alzheimer's but has no effect whatsoever on the underlying disease process. The overall research success rate for the whole decade was just 0.4%. This means that the rate of failure was a staggering 99.6%, one of the highest failure rates for any type of disease research in the world. When it comes to slowing or stopping Alzheimer's disease, the current success rate is 0%. Alzheimer's research is the greatest and most costly misunderstanding of all. It doesn't take a brilliant neuroscientist to see that there's something very wrong with the way we're conducting research. How could we invest so much scientific knowledge and so much money? The NIH, National Institutes of Health, has spent hundreds of billions of dollars on Alzheimer's research and is projected to spend $991 million in 2017, only to fail over and over again. Why has this been happening for decades, and why do we stubbornly adhere to the same approach despite these glaring failures? The answer is simpler than you might think, once you understand how the research works. Coming up are the major misunderstandings about Alzheimer's that have impeded research and significantly delayed our search for a cure. Single molecule research. Modern medical research is fundamentally misguided when it comes to curing a chronic disease like Alzheimer's. Almost all our research is disease-based, meaning that scientists focus on developing a cure in the form of a single drug. The NIH, the main funding agency that determines which types of research receive financial support, adheres to a simplistic model that has guided medical research since the 18th century. Infection, bacteria, drug, outcome. This method has led to many spectacular breakthroughs. In the early 20th century, for example, our biggest killers were infectious diseases. Cholera took hundreds of millions of lives worldwide before an antibiotic was found. Now we know that a single dose of doxycycline can be used to treat this once dreaded disease. Cholera still affects developing nations today, as do other infectious diseases like malaria and tuberculosis, and that's why this model has persisted. Though treatment for these diseases may sometimes require multiple steps, the underlying principle is almost always a single drug designed to eradicate a specific infectious agent. When it comes to complex, chronic diseases of aging, especially diseases of the brain, this research method doesn't make sense. Acute infectious diseases like cholera usually involve one element that emerges and immediately damages tissue, invoking a strong immune response from the body. Chronic diseases, by contrast, represent years of cumulative damage that add up and become more and more complex over time. The problem is that scientists don't investigate this vast and multi-layered damage. Instead, they take a single myopic snapshot of the disease, usually one element in a much more complicated, much larger disease picture. In the case of Alzheimer's, this element is amyloid, and to a lesser extent, tau. There is indeed evidence that amyloid has something to do with Alzheimer's. Amyloid plaques were identified decades ago as we discovered the early onset genes implicated in Alzheimer's: presenilin 1, presenilin 2, and APP. It's clear that amyloid is propagated on some level as the disease progresses. But there are also many other processes parallel to amyloid that contribute to Alzheimer's, like inflammation, oxidation, glucose dysregulation, and lipid dysregulation. There is also ongoing confusion about amyloid versus tau in the progression of Alzheimer's. As far back as the 1990s, some researchers claimed that it was in fact tau intracellular tangles that were more closely associated with the symptoms of cognitive decline. New evidence suggests that tau tangles emerge later in the process and are better predictors of Alzheimer's and its progression than amyloid plaques. A 2017 study published by researchers at Mayo Clinic in the journal Brain concluded that tau may actually start the process of cognitive decline, meaning that drugs targeting amyloid may not be complex enough to treat or cure this disease. Despite the evidence we now have, scientists still seem blindly focused on amyloid, ignoring all other findings that don't conform to this single molecule approach. They're unwilling or unable to look at Alzheimer's as it really is, a complex, multifactorial temporal disease that requires a complex, multifactorial solution. This inability to understand the complexity of Alzheimer's has wasted billions of dollars and prolonged suffering for decades. Inadequate models. Alzheimer's drugs are developed and tested on animal models, mostly rats and genetically altered mice. In one sense, these animals are appropriate models for human disease because we share many genes in common. To date, roughly 4,000 genes in humans and mice have been studied, and fewer than 10 were found to exist in only one species. And yet these unique genes result in all kinds of biological differences, ranging from how genes are turned on and off to important qualities like lifespan. Mice live for 2 to 3 years. Their lifespan doesn't allow them to endure the kinds of stress a human does over the course of 70 or 80 years. They're not subjected to inflammation, oxidation, insulin resistance, and vascular assaults in the same way we are. They simply can't replicate the complicated biology of Alzheimer's in the human brain. The other major problem with genetically engineered mice is that they're designed to express the late-stage pathology of Alzheimer's, amyloid buildup and hippocampal atrophy, not any of the long-term pathways that also contribute to Alzheimer's: inflammation, oxidation, glucose dysregulation, lipid dysregulation. Mouse models may represent the same disease outcome, but the cause is not the same. Researchers are well aware that there is no commonality of pathways in genetically altered mice and humans, but they continue to work with the flawed model. This is why so many clinical trials fail. Our animal models don't come close to representing the disease we're trying to cure. In recent years, Alzheimer's models have progressed to some extent, especially with iPSCs, induced pluripotent stem cells. iPSCs are adult cells that have been genetically manipulated to become any type of cell we want to study: heart, liver, pancreas, brain. We can now take nascent cells from patients who had Alzheimer's and turn them into neurons. From these neurons, scientists create what are called neurolattices, mini brains that are grown from actual human tissue. While having a human genetic model is a huge step forward, these neurolattices still lack the three-dimensionality of the actual brain, as well as all the processes outside of genetics, like diet, exercise, and stress, that we know are so important to chronic diseases like Alzheimer's. None of the models we currently use are at all accurate representations of this complex disease. In mouse models, false amyloid lesions lead to false results. In neurolattice models, an incomplete picture leads to an incomplete treatment. As any scientist will tell you, an inaccurate model will only yield inaccurate outcomes. Assuming clearance equals restoration. Yet another flawed aspect of Alzheimer's research is the assumption that clearing amyloid and tau will restore cognitive function. Drugs are designed to attack amyloid. Mouse models are designed to express amyloid so we can figure out different ways to remove it. But by the time amyloid and tau have accumulated in the brain, hundreds of thousands of neurons have died. Brain structures have been permanently altered, and the overall volume of the brain has decreased. While removing amyloid and tau may have some minor but temporary effect on cognition, this approach will never be a cure. There's very little chance of restoring significant cognitive function once this much damage has been sustained. In most clinical trials, treatments are given to subjects with mild to moderate Alzheimer's, well after amyloid and tau have accumulated on top of all the other structural damage in the brain. This is why no drug designed to cure Alzheimer's has ever improved cognition. We need to intervene much earlier if we want to influence this disease, and we need to recognize that amyloid and tau are a small part of a larger picture, likely the result of trauma that has been mounting for years or even decades. Given the many limitations of our dominant research model, it's not surprising that Alzheimer's clinical trials have such a staggeringly high failure rate. To date, the only thing that has been shown to affect the curve of decline or slowed the progression of Alzheimer's is lifestyle change, which is the basis of the Neuroplan in Section 2. Not amyloid-clearing medication, not anything developed on a flawed mouse model costing billions of dollars and years of testing, but lifestyle change. We have a solution to Alzheimer's, and we have proof. So why aren't we doing what works? Why is the most hopeful means of preventing and slowing Alzheimer's almost completely ignored by both the research establishment and clinicians? One simple answer. There's a long-standing belief that an organ as complex as the brain can't be affected by lifestyle. Somehow the brain is outside of the body, subjected to a different set of rules. This couldn't be further from the truth. As we explained earlier in this chapter, the brain is the end organ that receives all the stress and trauma, or conversely, all the resilience and resistance from other body systems. Each lifestyle chapter in this book will show you in detail how the brain is part of the body, and how when we harm the body with unhealthy lifestyle choices, we also harm the brain. The more troubling answer is that the research establishment has given up on lifestyle intervention without ever even attempting it. And this is in spite of many researchers who now acknowledge that lifestyle does in fact influence Alzheimer's and dementia. The NIH, the National Science Foundation, NSF, and similar leading research organizations categorically reject the possibility of lifestyle change. They just don't think it's worthwhile. They claim that behavioral change is difficult, if not impossible, for the general public, and that lifestyle protocols invariably fail to create lasting change. Though a small amount of funding is allocated to simple interventions in order to study the effects of lifestyle on cognitive health, a specific diet, for instance, or a basic exercise routine, these interventions are never comprehensive and thus never have a chance of illuminating the power of lifestyle. The real money goes to single-molecule studies, which are deeply flawed in all the ways we previously discussed. Even if some researchers wanted to study the disease more broadly, they wouldn't be able to secure funding for multifaceted, multivariable research. The funding, of course, comes from pharmaceutical companies interested in patenting pills, and from grants awarded exclusively to researchers who believe in the single-molecule model of chronic disease. Anyone who's gone to a primary care doctor or neurologist knows that this attitude pervades clinical practice as well. Doctors aren't trained in prevention. They go through 12 years, or more, of advanced training in disease identification and management, with perhaps an obligatory lecture or two about prevention. This hyper-focused, myopic approach to overall health teaches doctors not to believe in anything beyond their education, and that's why almost all of them reject the notion of prevention and behavioral change. Most physicians have never seen an example of well-designed, effective lifestyle intervention, and the healthcare system affords them no time or space in which to attempt it. The average primary care doctor spends between 10 and 15 minutes with each patient. The few doctors who do want to address lifestyle run out of time, or simply don't know how. Every patient suffering from cognitive decline should be informed of the many lifestyle risk factors, yet almost none are. And because of doctors' all-knowing, inflexible approach to medicine, patients are often too intimidated to speak up and ask questions. A few brave scientists have pursued lifestyle research despite the overwhelming barriers, and the data that we now have is truly remarkable. Proper nutrition and exercise significantly lower your risk of progressing from mild cognitive impairment to dementia, and also decrease your chances of developing cognitive decline in the first place. And yet the amount of media coverage and scientific interest is negligible. This is not a conspiracy. It's simply a cultural disconnect. The research is flawed, the clinical application is flawed, and our understanding is flawed. But if we can change our understanding, if we can unpack the myths and misunderstandings about Alzheimer's, we can revolutionize the way we fight this disease. The solution in plain sight. Despite all the myths and misunderstandings, the failed clinical trials and misguided theories, there is a way forward. Research points unequivocally toward lifestyle intervention as the cure for cognitive decline. We learn more every day about how our behavior impacts the health and resilience of our brains. People are growing frustrated with the conventional approach to health care, especially when it comes to Alzheimer's and dementia. Awareness is growing and the system is changing. Progressive medical practitioners are increasingly interested in finding the cause of a disease instead of merely medicating symptoms and risk factors. For almost every chronic disease, the root cause can be traced back to an unhealthy lifestyle. And when patients change their lifestyles, they experience a decrease in all types of chronic disease. We also have a precedent for how to study lifestyle change and implement it in clinical settings. Thanks to Dean Ornish's incredible lifestyle heart trial in 1990, we now know that heart disease, America's #1 killer, can not only be prevented, but also, in most cases, reversed with a plant-based diet, moderate exercise, and stress management. Another study found that people following healthy lifestyles experienced more than a 90% decrease in the risk of developing heart disease. The same goes for diabetes. Studies now show that plant-based diets both decrease the risk of developing diabetes and improve blood sugar levels. A landmark study published in the New England Journal of Medicine in 2002 found lifestyle intervention was more effective at reducing the risk of diabetes than the standard medical treatment. A follow-up study conducted 4 years later found that participants were able to sustain their lifestyle changes and reduced diabetes risk even after lifestyle counseling had been completed. In other words, they stuck to their new way of living and stayed healthier as a result. New research is also uncovering these same lifestyle effects on cancer treatment and prevention. There are now hundreds of research projects and plenty of funding to support studies on lifestyle, cardiovascular disease, diabetes, and cancer, and doctors routinely suggest lifestyle changes for patients at high risk for these chronic diseases. It's only a matter of time before we're having these same conversations about lifestyle and Alzheimer's. And in the next chapter, you'll learn about the indisputable research that proves this connection. We see hope in the lifestyle research on cardiovascular disease and diabetes. We see hope in the widespread acceptance of factors other than genetics that put us at a high risk for developing chronic diseases. And most of all, we see hope in our patients. We don't agree that people are lazy or incapable of change. The people we meet every day are terrified, and they'll do just about anything they think will help. In our practice in Loma Linda, we've observed a proactive attitude toward this disease, a need to take control and face Alzheimer's head-on. The problem, though, is that our patients exert effort in all the wrong ways. They're convinced they can find a solution through vitamins and supernutrients for the brain. They spend billions of dollars on brain games. They join elaborate, intensive exercise programs when their exercise quotient for the day is only 20 minutes. They take their loved ones to renowned hospitals to consult with the nation's top neurologists, when all the while the solution is at home, in their refrigerators. But no one has told them this. No one has taught them about lasting behavioral change. No one believes that they're disciplined or motivated or intelligent enough to truly live a healthy life. This book offers a different perspective. We know the current approach isn't working, and we don't have time to lose. Why ignore all the powerful lifestyle research we now have? Why assume that people can't change? That a well-designed and effective lifestyle protocol couldn't usher in a new way of thinking about chronic diseases like Alzheimer's? The NIH is right that lifestyle intervention presents a challenge, but as we'll prove to you in the coming chapters, it's the only solution for brain health, and with the help of our Neuro Plan, it's achievable for everyone. Chapter 2. The Power of Lifestyle Medicine. The myths and misunderstandings about Alzheimer's disease and dementia can be overwhelming, even devastating when you think of the wasted time and money of countless doctors, patients, and caregivers. But this book is called The Alzheimer's Solution for a reason. In this chapter, we'll present compelling data that proves Alzheimer's and dementia are deeply influenced by lifestyle factors like what we eat, how often we exercise, and the quality of our sleep. While it may be easier to blame a devastating disease like Alzheimer's on a single gene, this false belief is killing millions. The truth is much harder to accept, that we are bringing Alzheimer's and dementia into our households through the choices we make every day. But the truth is also liberating because it puts control back in our hands. Loma Linda. The first thing we noticed was the food. We'd stopped at the hospital cafeteria after our interview at Loma Linda University, expecting to see the usual fare. Anyone who's spent time in a U.S. hospital knows that most cafeteria food is extremely unhealthy. There might be an obligatory salad bar, but you can also order burgers, fries, greasy pizza, sugary desserts, basically your pick of the least healthy food available, and the exact opposite of what you should be eating if you're sick. But at Loma Linda, there were roasted vegetables, organic sandwiches, nourishing soups. Everything was vegetarian, and the healthiest items were marked living whole, so people could make informed choices. Across the street, we found the Loma Linda Market, which offered a large selection of fresh produce along with bins of nuts, grains, and beans. There was no meat section in the store. A few buildings over stood one of the largest, best-equipped gyms we'd ever seen, and at the very heart of the community was the church. The doors were open, and we could see people of all ages taking a moment out of their day to practice the faith that sustained them. Then we visited a local nursing home and met Margaret, a 102-year-old woman who walked 3 miles a day. She didn't just walk, she power walked. She also shopped for her own groceries, volunteered in the Seventh-day Adventists Church, and knew the names of all the nurses and other residents. Many elderly people in their 80s and 90s have a noticeable slowness of thinking, but Margaret was as sharp in conversation as a woman half her age. She embodied the totality of a healthy lifestyle. She ate a plant-based diet, exercised regularly, served her community, and she was surrounded by others just like her who led fulfilling lives well into their 90s and beyond. Loma Linda, California, a small city located 60 miles east of Los Angeles, is widely considered one of the healthiest places in the world. A third of its roughly 25,000 residents are Seventh-day Adventists whose faith is deeply connected to health and wellness. The religion celebrates vegetarianism, regular exercise, stress management, and community service. Smoking, drinking, and even caffeine consumption are discouraged. This unusually healthy lifestyle results in the Adventists living, on average, 10 years longer and healthier than the general population, a statistic that has made them famous worldwide. Since the 1950s, organizations like the American Cancer Society and the National Institutes of Health have looked to Loma Linda for answers to the chronic diseases that have exploded elsewhere but seem to have left this community relatively untouched. The research that has emerged over the decades has given us profound insights into the relationship between lifestyle, longevity, and the avoidance of chronic disease. A 2007 study found that Adventists who ate a plant-based diet free of eggs and dairy had a lower risk of obesity than both vegetarians who ate eggs and dairy and non-vegetarians. The prevalence of diabetes was 2.9% in vegetarians versus 7.6% in non-vegetarians. Overall, vegetarians had roughly a 50% lower risk of developing diabetes in their lifetime compared to non-vegetarians. Another study of the Adventist population found that vegetarians had a lower risk of developing all types of cancer than non-vegetarians. The risk of female-specific cancers was up to 34% lower in vegetarians. In a 2003 study published in the American Journal of Clinical Nutrition, researchers from Loma Linda University compared 6 studies on low meat consumption and lifespan with the Adventists' health studies, a series of long-term studies that look at lifestyle and disease in over 96,000 individuals. They found that people who ate a predominantly vegetarian diet had a longer lifespan in 4 of the 6 studies, and identified no positive or negative associations between meat and longevity in the other 2 studies. A 1993 study titled "The Incidence of Dementia and Intake of Animal Products" found that in a group of over 3,000 individuals, those who ate meat, including those who ate only poultry and fish, had twice the risk of developing dementia compared to vegetarians. Numerous other studies have found similar associations between the way of life in Loma Linda and the avoidance of some of our most feared diseases. Loma Linda is also America's only blue zone, a term popularized by Dan Buettner in The Blue Zones, his best-selling book about lifestyle and longevity. Blue zones are communities in which people live measurably longer and healthier lives due to optimal nutrition, exercise, stress management, and social support. As Buettner explains, the 9 tenets of healthy living in blue zones are 1. A lifestyle that involves natural movement throughout the day. 2. A deep sense of purpose or meaning. 3. Skillful stress management. 4. Avoiding overeating and eating late at night. 5. A primarily plant-based diet. 6. Enjoying a drink or two with friends, though many Adventists abstain from alcohol. 7. Connection to a faith community. 8. Living near family and finding a lifelong partner. And 9. Access to social networks that support healthy living. Communities with such a comprehensive healthy lifestyle are exceedingly rare. There are only 5 in the world: Sardinia, Italy; Okinawa, Japan; Ikaria, Greece; Nicoya, Costa Rica; and Loma Linda, California. Buettner's groundbreaking research on behaviors common to these diverse cultures has since inspired researchers to investigate the underlying science. Cities across the world have adopted features of the Blue Zone lifestyles, hoping that the residents can reduce their risk of chronic disease and experience the same incredible health and longevity. We were at a crossroads in our medical careers when we discovered Loma Linda. We'd made our way through medical school, knowing that neurology was our calling, and then embarked on residencies and fellowships where we could participate in cutting-edge research. We still believed that the only hope for chronic diseases like Alzheimer's was a pharmacological cure. Both of us were steeped in the individual mechanistic view of Alzheimer's and dementia, the same flawed approach to research we described in Chapter 1. But we were growing increasingly uncomfortable with it. Aisha was a research assistant and coordinator for a UC San Diego study that used functional MRI to look at Alzheimer's-related changes in the brain. Participants with a family history of dementia were tested in their 50s and 60s, and though the implication was that Alzheimer's could be seen as it developed, no interventions or treatment were part of the study. As Aisha reviewed the brain scans, she would see that some of these individuals had early signs of Alzheimer's, and yet there was nothing she could do. She knew these people would eventually develop the disease, and that it would progress until it took their lives. There was no way to stop it or slow it down. Everyone around her kept repeating what she'd been taught. Alzheimer's disease cannot be prevented. Dean had a similarly disillusioning experience as a fellow in the experimental therapeutics branch at the National Institutes of Health. Working on numerous clinical trials, he saw a mechanistic approach that didn't consider the whole person, the whole disease, the whole complex process over time. He gave Alzheimer's patients medications that targeted singular pathways, while he and all the other researchers knew the disease was far more complicated than that. He cared for patients suffering from many different types of dementia, including progressive supranuclear palsy, a neurodegenerative disease with Parkinsonian features and dementia, who received infusions directly into their brains via cellular implants. All these trials failed. It didn't matter if the treatment was a pill or an antibody or an invasive brain procedure. Nothing seemed to work. The research was going nowhere, but it wasn't nearly as frustrating as clinical practice. We could offer our patients little beyond a diagnosis. We had to tell them their disease had no treatment, and with each look of dread on their faces, each family member taking in the horror of what was happening to their loved one, we grew more and more defeated. The realities of the profession started to sink in. We were stuck in a disease-based system that had almost nothing to do with health, and yet we never considered giving up. We'd made it our life's work to search for a cure to this devastating disease. We'd met as young physicians volunteering abroad, and in our first conversation, we learned that both of our grandfathers had suffered from dementia. This was the journey we were meant to take. But we kept wondering whether there was another approach, a way to reach people and make a difference before their symptoms emerged and nothing could be done. One night while we were still at UCSD, we attended a talk by Dr. Elizabeth Barrett Connor, the founder and principal investigator of the Rancho Bernardo Heart and Chronic Disease Study. She and her team of researchers had collected data on lifestyle and cognitive function in men and women for over 20 years. They'd found gender differences in elderly populations with cognitive decline, and had also discovered associations between dementia and both smoking and alcohol consumption. Listening in the audience that night, we were intrigued by what Barrett Connor had learned about habits and behaviors that put us at a high risk for Alzheimer's and dementia. We wondered how much literature existed about the risk factors for cognitive decline. We began doing systematic reviews of publications in peer-reviewed journals, collecting decades of studies on the connection between lifestyle and chronic diseases like heart disease, stroke, diabetes, and cancer, hoping for insights into risk factors that also played a role in Alzheimer's. One study showed that eating nuts lowered the risk of heart disease, another that fruit consumption lowered the risk of lung cancer. The Nurses' Health Study and the Health Professional Follow-Up Study showed us that every incremental increase in fruit and vegetable consumption lowered the risk of stroke by 6%. A separate analysis of the Nurses' Health Study found that women who ate a predominantly Mediterranean diet high in fruits, vegetables, legumes, nuts, and fish had a 29% lower chance of stroke compared to those who ate predominantly a Western diet high in sugar and processed foods. The Cardiovascular Health Study revealed that obesity in midlife increased the risk of dementia by 40%. Scientists at Columbia University concluded that high insulin levels in elderly people could account for 39% of Alzheimer's cases. All these chronic diseases seemed to be related. What was good for the heart and kidneys also appeared to be beneficial for the brain. A whole food, plant-based diet was by far the best dietary pattern for fighting each one of these diseases. Not a single study showed any benefits of eating meat. The more we thought about it, the more sense it made. The body is a collection of interconnected systems, and the brain is itself a system. Why wouldn't it be affected by what we eat, how much we exercise, our overall state of health? People with healthier lifestyles were often able to avoid other chronic diseases. What if there was also a way to avoid Alzheimer's and dementia? A few months later, we read The Blue Zones and realized there was an epicenter of healthy living just next door. So much had been published about Loma Linda and heart disease, diabetes, and even cancer. But there were only a few early studies related to dementia. No research on Alzheimer's and the Loma Linda population had been published in nearly 10 years. We wondered if anyone had looked further at the association between cognitive decline and lifestyle. Was it possible to replicate the previous results, or learn more about which healthy behaviors afforded the most protection? And if there were a clear association, wouldn't we have heard about it by now? We knew that studying lifestyle would put us at odds with the research establishment. Our mentors warned us that we'd be risking our careers, our reputations as clinicians and researchers. But at the same time, we knew that if we dedicated ourselves to the same myopic approach, we would never contribute something of value or actually help our patients. To us as physicians,